Single slit interference is the idea that waves from a single source can interfere with themselves. And you're like, what the what? No way, really? And yeah, really. So this is something that was a surprise to many. But let's think about how this is going to work out. So first of all, we've got some language we've got to get out of the way. When we talk about the bending of waves, because that's something that people like to talk about when they talk about light and traveling through a medium or something like that. We talk about the word bending of waves. Now in grade 10, we may have talked about refraction, and that's the changing of a wave's direction when it goes from one medium to another based on the speed of the two different media. This is different. This is called diffraction, okay? So the bending of waves around corners past an obstacle or through a gap or a single slit causes diffraction. And just to make sure that there's no doubt about how we're spelling this, this is diffraction. Okay? Not refraction. Totally different. Okay? And in grade 10, I had to say, oh, refraction and reflection are not the same thing, because, oh, they both start with an R and end with a shan. No, this is definitely not the same thing. Okay, so let's think about how this is going to play out. As you have ripples that pass through a barrier, and we've got this little opening here, and you can imagine that if I had this lined paper here, this lined paper represents incoming ripples, like wave fronts approaching this wall, okay? And as they smack into this wall, most of the waves get blocked, but some of the waves are allowed to transmit through the gap. Cool so far? I just happen to have lined paper that kind of looks like waves, okay? So I'll pull that away, and as it comes out the other side, we get this kind of curving effect. And so I'm going to do a little bit of circling. So let's circle this bit here and point out that I can see that there's curved edges. And I'll say it's due to diffraction. Really, it's an example of diffraction. And we can look at a video later, but people might say, well, how did you capture this image? Well, actually, this is water waves, and this is water waves that were being transmitted up to a wall, and it was being done over top of a sheet of glass, and there was light projecting downwards, and this is the shadow of what was happening. So you can imagine this is just the shadow of waves being projected down onto paper. You guys imagining that so far? Okay, so the nice thing about water waves is that they're a decent model for what happens with other waves, right? In this case, electromagnetic waves, because that's what we're working towards here with the idea of light waves doing the same thing. Now, if I talk about patterns, I say, hey, right here, notice that it's really, really pronounced wave patterns. So because it's really pronounced, I want to propose that this is bold constructed interference. Constructive interference. The waves are getting built up. They're very strong. Notice right here, I've already circled this part, but I'm going to label it a second thing. I'm going to say that it's kind of gray, but the fact that the waves aren't very pronounced there tells me that destructive interference is happening. You guys with me so far? If it's pronounced, constructive. If it's kind of torn down, it's destructive. And then over here, if you notice, it's probably easier to see in the spot that I haven't scribbled on. You notice how it gets gray and then it gets more pronounced again, but not as pronounced as the central part. Do you see what I'm talking about? Okay, so I'm going to circle this again, and I'm going to call it faint constructive interference. Maybe I should put quotations around these because those aren't really scientific words. I'm just trying to be qualitative in my description. So faint constructive interference. Constructive interference. And what we were talking about previously was how this would kind of relate to if I was shining lasers, because lasers are a good example of coherent light waves. That is, all the light is synced up with each other. And so here I want to draw a diagram that kind of reminds us of what we were talking about with two-slit interference. And I want to say, hey, as this laser beam, I got peaks and troughs. Peaks are the solid line, troughs are the dotted line. But as these peaks and troughs, these waves, approach that barrier, there's an opening, an aperture. And what this diagram over here says, I'm just going to rotate it sideways, is that we're going to have waves that come out the other side with a curvature to them. Diffraction. But there's going to be sort of a gap. Whoa, my voice changed there. Kind of a gap. And see that gap? That's the destructive interference. That's where the waves are not being built out, the grayed out zone, if you like, okay? And if this was light waves, what would it look like when it smacks into a screen? Well, we got to draw a screen in place here. So, hey presto. Oops. Presto card for my projection screen. And it gets projected onto a screen, and what these waves, if they're light waves, would look like would be relative intensities, relative brightnesses. Well, if this is a fainter constructive interference, that's going to be dimmer light. It's going to smack into the screen there. Then there'll be a dark space because of destructive interference, and then it'll be brighter light. And so this is actually an intensity graph. I'll label up the axes in just a second. And then dimmer light again. You know what? I think I'm going to rotate this because I want to make sure that we have this idea that waves have been projected, hit a barrier, gotten through an aperture, they've diffracted, there's been some sort of interference that's occurred to allow there to be destructive interference along this axis, and I can draw in the destructive interference line. Projecting darkness, well, failing to project light, but a dark spot would be on the screen. And then there would be a constructive interference that would be along that axis, constructive interference along that line, and then what gets projected onto the screen in terms of relative intensity, so I'll label this up as intensity. I'm not going to put units, it would be like watts per meter squared or something like that, but the vertical axis, if this was a graph, is going to be intensity. And then this axis is actually a spatial axis, so it's along, the surface of a screen. And people actually have names for this. So they'll talk about CBR, the central bright region. And I mean, there's a news feed that I subscribe to that's called the CBR. I guess it's like this play on words where, if you've been illuminated, then you've been enlightened by things or something. So you should always try to live in the central bright region of science or something. But the central bright region, the CBR, is this large lit up spot in the middle. Okay, then we have a destructive interference spot, and then we have another lesser bright spot on either side. And notice again, just like two-slit interference, it's symmetrical, right? So we have this symmetrical thing that happens. We haven't even talked about what gives rise to this, but it's such a thing that's a pattern that people want to make sure that they recognize that it's a thing. Okay, now if you shine light through a slit, you end up getting stripes of bright and dark. If you shine light through a pinprick, you'll actually produce rings of light and dark. And that's kind of a neat thing when it comes to Compton scattering, which is what this is all about. And people say, well, why would you care about that? Well, it turns out, because people always like to have a practical application. We're going to talk about the theory, don't worry about that. But one of the practical applications is that if I can make use of a single wavelength to figure out how the constructive and destructive interference spreads through this crack, I bet you I could calculate either how long the wavelength is based on the size of the crack, if the crack is a known value, or if I knew how long my wavelength is, and by the way, every helium neon red laser, we know its wavelength. if we knew the wavelength, then we could calculate how big the crack is. And so this comes into a great application. I mean, hey, 100 years ago, people were like, wow, this is a neat effect. These days, people use this for materials quality inspection. We can shine radiation at a material that we'd like to have no cracks in, or we'd like to know how bad the cracks are, or we can shine radiation at a material that has pinpricks in it, and based on the interference pattern that comes out the other side, we can make measurements about how big those imperfections are. Does that make sense to everybody? Okay, so I'm kind of front-end loading this with the why would I care? Why would I care? Because it shows that light has wave properties. Also, in the more practical everyday of today times, why would I care? Because this allows me to investigate things like something that I'd like to send to space and not have break apart in transit. Or maybe it's something that's, I don't want to like trigger people with military stuff, but maybe it's something that's got to carry a heavy military payload and we'd like to have it not blow up in transit. Like this is stuff that people would care about. And yes, that kind of materials testing really does happen. Or it could be something more mundane, like maybe I've got a manufacturing process at my auto plant for an internal combustion engine, and I just really, like, I want to check to see if this thing's going to crack apart over time after, 1,000 hours of use or something like that. Maybe it's that. Anyway, we got lots of different things we could use this for. Let's talk about the theory a little bit more. So there's this old time idea called Huygens wave construction for plane waves. Now you can do your own historical reading on this one for Huygens and why he did what he did, but let's just say we have this diagram that's still useful for us today. I'll kind of redraw what we had before, where we have a slit that has a width, so I'm going to let W represent the width of that slit, that opening in the barrier. The waves come out the other side with diffraction clearly visible, the curvature of the projected waves coming out the other side. It doesn't change the wavelength. Notice that I'm keeping my primary constructive band and my secondary constructive bands the same wavelength. I'm keeping them the same separation for wave fronts. But what Huygens said was I'm trying to say it the way that the man would have said his own last name. Most English speakers are going to say Huygens principle, okay? Huygens, potato. All right, not really. If it's your last name, it really does matter. But if you hear other people saying it, they'll probably say Huygens principle. Anyway, every point on a wave front acts as a source of a secondary wavelet. A secondary wavelet. Talk about what that means in just a second. Which travel with the speed of the wave, okay? And at some subsequent time, the envelope of the secondary waves represent the new position of the wave front. Well, what the heck does that mean? Let's draw a picture. For Huygens principle. So I want to try and use this idea to redraw this diagram in a Huygens kind of way. I want to have myself a barrier. Make it nice and pronounced. Now imagine if you're somebody well before lasers, so before the 1970s, maybe you're in like the 17 or 1800s, and you're looking at a harbor, and the ocean waves lap up against the harbor, and if you're not from any kind of like nautical family or whatever, maybe you don't really have an appreciation for why this is important, but harbors would typically have like a narrow opening that you would bring the boats into, and then there'd be an inner harbor, like where you could keep the boats where the waves would be diminished. And if you were to watch such a situation, you might see a boat approaching that opening. And it would be bobbing up and down with the waves. And this opening would have a width, I've already labeled it up above, a width of W. And as those waves get through, the waves are going to end up doing exactly what we're saying. They're going to create this wave front that gets transmitted easily through the center, that central bright region, as we've been calling it with the lasers. It's a water wave we're talking about right now. We're just trying to predate lasers in terms of our thinking, because this thinking came be well before lasers, because people have been using harbors for centuries. And then there would be these other little wavelets off to this, or wave fronts off to the side. But this doesn't actually add the Huygens part to it. What Huygens said was, if I zoom in here, let's see if we can get a hold of this picture a little bit more detailed. Oh, try and get that in focus. Oh, we got this. All right, by the miracle of optics. All right, so what Huygens said was, if I have a wave front, then this wave front could be thought of as really infinite. You guys have talked a little bit about limits in math class, but imagine there being a whole lot, anyway, of little wave fronts. Or not little wave fronts, little point sources, an infinite number of little point sources. And each one of those little point sources for a wave is going to produce its own. Imagine if it's a point source for a wave, doesn't it make a semicircular ripple? And then the next one makes a semicircular ripple, and then the next one makes a semicircular ripple, and then the next one makes a semicircular, and so on. And see how the front edge of those semicircular ripples all kind of line up? Where they line up is where the next wave actually happens. Now, if you want to be like a chemistry person, people are always like, oh, for water, does that mean that every one of those dots is like a water molecule? You could try and go down that rabbit hole. It's not important, it's not material for this, because remember, electromagnetic waves aren't transmitted by vibrating particles, so that's not actually like necessary for this model. We're just saying that every point in space along a wavefront represents a virtual spot that a point could have caused a ripple. And if all of those points could cause ripples, then all of the leading edges of those ripples would line up along the same line, and we call that the wavefront for the next propagated cycle of the wave, okay? And we say, okay, well, then going on with that, that means that there, all the way, all these wave fronts are made up of infinite point sources. Cool. So what's the deal with the constructive and destructive interference? Well, right at this width here, can you imagine that at that point there, there's going to be some number that's less than the larger infinity of point sources? Some smaller number of point sources. I mean, I'm saying infinite, so this must be a smaller number of infinites. But somehow those are point sources. And those point sources are going to have to interfere with each other. And according to Huygens' principle, it seems like that's going to cause constructive and destructive interference. This is the model that we're working with. And people say, well, okay, you wouldn't let us before need there to be water molecules being the point sources. There must be something being the point sources. It turns out that it's individual photons when it comes to lasers. Maybe we could talk about water molecules. Somehow there's point sources there that are causing this interference. That's the mental leap that we're being asked to make. It's a decent leap, right? So these point sources are causing interference, constructive and destructive interference. And the reality is, and Huygens would have noticed this, is that if I put a boat here, isn't that boat going to be able to move quite freely? It won't be bobbing up and down. It can just travel to wherever its destination is without having to worry about rocking the boat, so to speak, you know? Whereas another boat that maybe is like in the central bright region, this boat's just going to be bopping around like crazy. And if you're talking about interior harbors, that's going to map out where you should go to go to dock, right? In fact, inner harbors have yet further inner harbors. And you can imagine if you built a seawall, and within that seawall you built chambers. Here's an opening to another inner chamber within the docking system. Here's another opening to an inner chamber within the docking system. Can you imagine that I probably wouldn't want to choose this opening to get into the inner docking chamber? See how it would be like all wavy? There'd be lots of incident waves, constructive interference. I definitely wouldn't want to choose a spot right here because this is where there's going to be a big splash zone, right? Lots of waviness at this point. You can project it where the central bright region is going to smack up against that wall. And so it makes sense to direct boats over to here so that they can go into yet an further inner harbor. You see how this works for docking? And sometimes this is why the science of how things works isn't applicable until later for other things, right? I mean, this is something that might have been noticed for docking your boat, but it also turns out to be useful for lasers. definitely not how it was developed in the first place, right? So people sometimes say, well, why are you developing this research or whatever? It's not even applicable today. Turns out maybe not. Sometimes it's just cool to notice stuff, right? In this case, good for docking. Now, when these waves do hit that inner opening, the one that was maybe the bad docking spot, it actually turns out that that inner opening acts as yet another diffraction aperture, and it does cause ripples into that chamber as well, right? And you can imagine if you're playing in a swimming pool or in a bathtub, ripples over here are going to ripple outwards, and then if you put a partition like this, they would ripple into the inner chamber as well. Like, I mean, we can play this kind of mental game in our mental bathtub, right? So let's do a couple of other little additions to this. We know that the wavelength for a given wave source is going to be fixed, but I want to propose that this works best, in fact, is really easily shown when the wavelength is greater than the width of the opening. That's when we're going to say that single source interference is in play. And the other thing we're going to say is that when the wavelength is much, much larger than the slit, the diffraction seems to be semicircular. So that's kind of a limits thing. Oh, sorry, here I am. I got to zoom out more, but I'll slide over. And what I mean by that is this, with the second statement, is that when I have a partition, like this one that I'm drawing, if the waves are really big compared to the partition, and I'm not even exaggerating it enough right now, then the ripples that come out the other side will look like semicircles, you know? And we don't get this like obvious diffraction interference issue come up. Yep.
For the diagram there, like how come it has the dotted lines? The other ones like don't.
Oh, you know what? Here I was just, in my imagination, I was thinking about peaks and troughs. So dotted lines were troughs and solid lines were peaks.
Okay.
Yeah, it's not that I was trying to like be different or show something extra. I guess I just like was on autopilot there and I was drawing waves the way I pictured them from overhead. Yeah, that's a good question. Oh, and nobody's going to complain about this too much. I didn't add in these dotted lines, and the wave length isn't supposed to change. So I guess this would be like a solid and this would be a dotted line, because I'm trying to preserve the wavelength when it goes from the outer chamber to the inner chamber, because it's not really two different media, so the speed of the wave shouldn't change either. And since the speed doesn't change, then the wavelength shouldn't change.